morning was perfect. 66 million years ago, the last morning of the Cretaceous period. Nobody knew it yet. The sun rose over what would one day be North Dakota. Warm, clear, the kind of day where nothing seems wrong. Dinosaurs were everywhere. They'd ruled Earth for 165 million years. That's hard to imagine. Modern humans have been around for maybe 300,000 years. Dinosaurs had 165 million. They weren't struggling. They weren't dying out. That's a myth people used to believe. The fossil record shows something else. Dinosaurs were doing fine, thriving actually. T-Rex hunted in the forests. Triceratops grazed in herds. Pterosaurs soared overhead. In the oceans, mosasaurs hunted like killer whales. The world was full of life. It was a Tuesday morning. Well, not really. Days of the week didn't exist yet, but it was morning. The sun was up. Animals were waking, starting their day. A young Triceratops drinks from a river. She doesn't know she has 6 hours to live. Maybe less. A T-Rex sleeps in the shade. He'll never wake up. Somewhere a pteranodon glides over the ocean, wings spread wide, riding the thermals. This is the last time anything will fly like this for millions of years. The world hums with ordinary life. Insects buzz, birds sing, small mammals hide in burrows. The day feels eternal, like it will never end. But 1,800 miles away, something is coming. You can't see it yet. It's still in space, moving at 45,000 miles per hour, faster than anything on Earth can imagine. It's been travelling for millions of years, a chunk of rock and metal 6 miles wide, about the size of Mount Everest. For its entire journey it's been heading here, to this exact spot, this exact moment. The dinosaurs don't know. They can't know. There's no way to see it coming, no way to understand what's about to happen. The Triceratops lifts her head from the river. Water drips from her beak. The T-Rex shifts in his sleep. The Pteranodon banks left following. The coastline. And in space, invisible, silent, the asteroid crosses the orbit of the moon. 4 hours to impact. I think about this sometimes. That last perfect morning. How normal it must have felt. How the world seemed solid, permanent, like it had always been and always would be. But permanence is an illusion. Everything ends. Even 165 million years of dominance. Even the rulers of the entire planet. The thing is, they had no warning, no chance to prepare, no way to understand that this was the last morning, that in a few hours everything would change. The sky was blue, the sun was warm, life continued, and something was coming. 3 hours left. The asteroid is closer now, still invisible, still silent, but closer. If you could see it, you'd notice something strange. It's glowing, just slightly. The friction of space dust hitting its surface at 45,000 miles per hour creates heat. Not much, but enough to make it shimmer. It's heading for the Yucatan Peninsula, what's now Mexico. Back then, it was shallow sea, warm water, coral reefs, fish everywhere. The impact point is already determined, has been for millions of years. The math is locked in, trajectory, velocity, angle of approach. It's coming in at about 20 degrees. Not straight down, that matters. A steeper angle would be worse. More energy directed into the ground. But 20 degrees means the asteroid will skip slightly, like a stone on water. Except the stone is 6 miles wide and travelling at 45,000 miles per hour. 2 hours left. On Earth, life continues. The Triceratops has moved away from the river. She's grazing now. Ferns, low plants. Her beak clips them efficiently. She's done this 10,000 times. She'll never do it again. The T-Rex is awake, hungry. He's tracking something. A hadrosaur, maybe. Something large enough to be worth the energy. He moves slowly, carefully. Predators are patient. In the ocean, a mosasaur surfaces, breathes, dives again. The water is clear. You can see 30 feet down, schools of fish dart past. Ancient sharks patrol the depths. Above it all, pterosaurs circle. Some have wingspans of 30 feet. They ride the air currents, barely flapping, just gliding, efficient, beautiful. Everything is normal. Everything is fine. 1 hour left. The asteroid crosses into Earth's atmosphere. Not the thick part yet, just the outer edge, the very top layer where air becomes space. It's moving so fast that the air can't get out of the way, can't flow around it. The molecules just compress, squeeze together, and when air compresses that fast, it heats up. The front of the asteroid starts to glow, really glow, white hot. The temperature climbs to thousands of degrees, but it's still too high up to see from the ground, still above the clouds, still silent. 30 minutes left. Now it's visible. If you knew where to look, a bright point of light in the sky, getting brighter, moving fast but nobody's looking. Dinosaurs don't watch. The sky for threats. Why would they? Nothing has ever come from above. Not like this. The asteroid is screaming now. The sound hasn't reached the ground yet. Sound is slow. But up there in the thin air the noise is incredible. A roar like nothing Earth has ever heard. The heat is intense. The air around the asteroid is plasma. Not gas anymore, not even fire. Pure plasma. The fourth state of matter. The same stuff that makes up stars. 15 minutes left. The Triceratops looks up. She hears something. Feels something. A vibration in the air. A pressure change. Her instincts say run. But where? How do you run from the sky? The T-Rex stops hunting. He feels it too. Something's wrong. Every animal on Earth is starting to feel it. A primal unease. A sense that something bad is coming. In the ocean, fish dive deep. Instinct. When danger comes, go down. But it won't help. Not this time. The pterosaurs scatter. They don't know why. They just fly. Fast. Away. Anywhere. 10 minutes. Left. Now everyone can see it. A second sun in the sky. Bright. Getting brighter. Moving impossibly fast. It's the size of a mountain. 6 miles across. Think about that. 6 miles. If you stood at one end, you couldn't see the other end. Too far, too big. And it's moving at 45,000 miles per hour. That's 12 miles per second. Faster than anything on Earth has ever moved. Faster than anything will move for another 66 million years. 5 minutes left. The sound arrives. A roar that shakes the ground. Trees sway, water ripples, every animal that can hear it freezes. Terror. Pure terror. Hardwired into every living thing. The sky is bright now. Brighter than day. The asteroid is a fireball. A streak of light cutting across the heavens. You can see it from 1,000 miles away. Birds fall from the sky. Just stop flying. Drop. The sound is too much. The pressure is too much. Their tiny hearts give out. Small mammals hide in their burrows, press themselves into the dirt, as deep as they can go. Some of them will survive. Not many, but some. 2 minutes left. The heat hits. Before the impact. Before the collision. Just the heat of the asteroid passing through the air. Trees burst into flame. Just ignite. Spontaneously. The thermal radiation is that intense. Forests that have stood for millions of years start burning. The ocean starts to boil. Not everywhere. Just directly below the asteroid's path. The water literally boils. Fish die instantly. Cooked. The coral reefs bleach white and die. 1 minute left. The Triceratops is running now, full speed. Doesn't matter where, just away. Her herd is scattered, everyone running. Panic, pure panic. The T-Rex has forgotten about hunting. He's running too, predator and prey running in the same direction, together. None of it matters anymore. The pterosaurs are miles away now, still flying, still running. It won't help. 30 seconds. The asteroid is huge in the sky, bigger than the sun, brighter than the sun. A mountain of rock and metal falling out of heaven. The sound is beyond sound now. It's not something you hear. It's something you feel. In your bones, in your teeth, in your chest. Your heart beats wrong. Out of rhythm. The pressure waves are that strong. The air is wrong, too hot, too bright, too loud. Reality is breaking. 10 seconds. The ocean below the impact point is gone. Not boiling anymore, just gone. Vaporized. Turned to steam. The seafloor is exposed. Bare rock, coral, dead fish. All visible for the first time in millions of years. And for the last time. 5 seconds. Every animal within 500 miles is looking up. They can't help it. The light is too bright. The sound is too loud. They look up and see their death coming, a wall of fire, a mountain, a god, something beyond comprehension. 3 seconds. The asteroid hits the atmosphere full force. The air can't move fast enough, can't compress anymore. It just shatters. The atmosphere itself breaks. A shock. Waveforms, expanding, a sphere of compressed air moving at the speed of sound. Everything it touches dies. 1 second. The Triceratops is still running. She'll die running. Never stopped, never gave up. The T-Rex has stopped. He's turned around, facing it, watching. He doesn't understand, but he's watching. The pterosaurs are too far away to see the impact, but they feel it. They'll feel it. 0. The asteroid hits the ocean at 12 miles per second, 6 miles wide, 6 miles deep, moving faster than sound, faster than thought. The ocean doesn't splash. It doesn't wave. It just explodes. 66 million years of dinosaur dominance ends in less than a second. The impact releases the energy of 10 billion Hiroshima bombs, all at once. In one spot. The explosion is visible from space, if anyone was there to see it. A flash of light brighter than the sun. A fireball 30 miles wide. The ground liquefies. Solid rock turns to liquid, then to gas, then to plasma. The impact crater forms instantly, 24 miles deep, 120 miles wide, the deepest hole ever punched in Earth's crust. And this is just the beginning. The shock wave expands, moving at 45,000 miles per hour, the same speed as the asteroid. It's a wall of compressed air, compressed rock, compressed ocean. Everything in its path simply ceases to exist. Not destroyed, not killed, just erased. The Triceratops vanishes. The T-Rex vanishes. The forests vanish. The mountains vanish. 500 miles in every direction. Gone in seconds. The impact throws debris into the air. Trillions of tons of rock, melted, vaporized. Some of it reaches escape velocity, leaves Earth entirely, will orbit the sun forever. Most of it goes up and comes back down, everywhere, all over the planet, burning, glowing, pieces of Mexico falling on Antarctica, on India, on what will one day be New York. Each piece is a meteor, thousands of them, millions, all at once, raining down, setting fires everywhere they land. Within an hour every forest on Earth is burning. The pterosaurs that flew away? They're burning now, mid-flight. The air itself is on fire. The small mammals in their burrows, some survive. The ones deep enough, the ones lucky enough, but most don't. In the ocean, a tsunami forms, not a wave. A wall, 300 feet high, Moving at 600 miles per hour, it crosses the Atlantic in hours, hits Africa, hits Europe, washes over continents, miles inland. Nothing survives. The sky goes dark, not slowly, instantly. The debris blocks the sun completely. Day becomes night and stays night for months, then years. The temperature drops fast, from tropical to freezing in weeks. Plants die, can't photosynthesize without sun. Herbivores starve, carnivores starve. The dinosaurs that survived the impact, they die now, slowly, in the dark, in the cold, all of them, every single one, except the birds, small, able to hide, able to survive on seeds and insects. They make it. 75% of all species on Earth go extinct. But here's the thing, here's what gets me. It was instant. The decision was made in less than a second. Impact, explosion, done. But the consequences took millions of years to unfold. The dinosaurs didn't know they were extinct yet. Some lived for weeks, months, maybe years, walking through the darkness, confused, hungry, dying slowly. The world ended in a second, but it took forever to finish ending. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching from and what time it is. I always check the comments, and it's fascinating. Someone in Tokyo at sunrise, someone in London at lunch, someone in California at midnight, all drifting off to the same story about the day everything changed. There's something comforting about that. Sharing this moment, this catastrophe that happened so long ago nobody was there to remember it, except we're remembering it now, together, across time zones, across continents, the same way those dinosaurs shared their last morning, not knowing, just living. Anyway, back to the shockwave spreading across the planet. The shockwave moves faster than sound. That's the first thing to understand. When the asteroid hits, it creates a pressure wave moving outward at hypersonic speed. The air itself becomes a weapon. Think about thunder. Lightning heats the air so fast it explodes outward. That's what you hear, a sonic boom from superheated atmosphere. Now multiply that by 1 billion. The impact releases energy equal to 10 billion Hiroshima bombs, all at once, in a fraction of a second. The air around the impact point doesn't just heat up, it turns into plasma, a state of matter hotter than the surface of the sun. This plasma expands outward in all directions, a sphere of destruction, growing at 15 miles per second. 15 miles every second. The Triceratops grazing 300 miles away has 20 seconds to live. She doesn't hear anything yet. Sound travels slower than the shock wave. The pressure wave will hit her before the noise does. She'll die in silence, or what feels like silence. The roar won't catch up until after she's gone. Here's what the shock wave does to the landscape. At ground zero, everything simply vanishes. The ocean boils away instantly. The seafloor turns to vapor, rock, water, life, all converted to superheated gas in milliseconds. The crater forms in seconds, 25 miles deep, 100 miles wide. The Earth's crust punches downward like someone hitting a drum. Then it rebounds, bounces back up, creates a central peak taller than Mount Everest, then collapses again. All of this happens in under 2 minutes. The shockwave races outward from this chaos. At 100 miles out, the pressure wave is still moving at 10 miles per second. Trees don't bend in the wind, they explode. The cellulose in their trunks flash heats and expands faster than the wood can handle. They burst from the inside out. Animals caught in this zone don't burn, they disintegrate. The pressure differential is so extreme that bodies rupture, lungs collapse, blood vessels burst. Death is instantaneous. Probably painless. The nervous system doesn't have time to register what's happening. At 300 miles, the shockwave has slowed to 5 miles per second, still hypersonic, still deadly. The Triceratops looks up. Maybe she senses something, a change in air pressure, a vibration in the ground. Animals can feel things humans can't. Elephants detect earthquakes through their feet. Birds sense magnetic fields. Maybe she knows something is wrong. The shockwave hits. She's thrown sideways, a 3-ton animal tossed like a leaf. The pressure wave lifts her off her feet and slams her into the ground 50 feet away. Her neck breaks on impact. She's dead before the sound arrives. The sound comes 3 seconds later. A roar so loud it would rupture human eardrums at this distance, but there are no humans. Won't be for another 66 million years. At 500 miles, the shockwave has spread out, weakened, but it's still powerful enough to flatten forests, knock down anything standing. The landscape looks like a bomb went off, which essentially it did. The T-Rex hunting in what will become Montana feels the ground shake. He's 700 miles from impact, far enough that the shockwave has lost most of its killing power, but not all of it. The pressure wave hits him like a wall of wind, hurricane force. He staggers, tries to stay upright. His prey, a hadrosaur, bolts in panic, runs blindly into a tree and breaks its neck. The T-Rex doesn't chase. Something is very wrong. The wind keeps blowing, harder than any storm he's ever experienced. The sky is darkening, not with clouds, with something else. Debris. Here's what most people don't realize about the shockwave. It doesn't just push air, it pushes everything. The impact vaporized rock, trillions of tons of it. This vapor shoots upward into the atmosphere. Some of it escapes into space. Most of it falls back down, but not right away. The debris cloud spreads outward with the shockwave, a curtain of molten rock droplets, each one the size of a marble, superheated to over 1,000 degrees. There are billions of them, trillions. They start falling about 20 minutes after impact. The first ones land in the ocean. The water boils where they hit. Steam rises in massive columns. The ocean surface looks like it's raining fire. On land, the effect is worse. Imagine standing in a meteor shower, except the meteors are the size of marbles, and they're everywhere, thousands per square mile, all burning hot. They ignite whatever they touch. Forests catch fire instantly. The trees are already damaged from the shockwave, broken, splintered, covered in sap and resin, perfect kindling. The fires spread faster than anything can run. A herd of Edmontosaurus, duck-billed dinosaurs, tries to escape. They're fast, can run 30 miles per hour, but the fire moves faster, driven by the wind, fed by the debris still falling from the sky. They die in the smoke before the flames reach them. Asphyxiation. The fire consumes all the oxygen. What's left is carbon monoxide and superheated air that sears their lungs. At 1,000 miles from impact, the shockwave is barely noticeable. A strong wind, a rumble in the distance, but the debris still falls. A pteranodon gliding over what will become Kansas sees the sky darken. She's been flying for hours, riding thermals, looking for fish in the inland sea below. The first droplet of molten rock hits her wing, burns straight through the membrane. She tries to compensate, adjust her flight. But more droplets fall. Dozens, hundreds. Her wings catch fire. She spirals down into the sea, hits the water and dies on impact. Around her, the ocean is filling with bodies. Fish, marine reptiles, other pterosaurs, all killed by the rain of fire. The shockwave keeps spreading. At 2,000 miles, it's just a pressure change, a shift in the wind. but the debris cloud is still there, still falling. The entire planet is being pelted with superheated rock. In what will become China, a herd of protoceratops huddles together. They're small dinosaurs, pig-sized. They live in burrows, underground dens where they raise their young. The adults sense danger. They push their offspring into the burrows, pile in after them. It's instinct. When threatened, go underground. It saves their lives. For now. The debris falls outside, sets the grassland on fire. But underground, the protoceratops are safe. The earth insulates them, protects them from the heat. They'll survive the first day, maybe the first week, but eventually they'll starve. There will be nothing to eat. The world above will be ash and darkness. But in this moment, they're alive, huddled together in the dark, breathing, waiting. The shockwave continues its journey around the planet. At 3,000 miles, it's barely detectable. A shift in air pressure, a distant rumble. But the effects are everywhere. The debris cloud has spread across half the globe. Fires burn on 3 continents. In Antarctica, which isn't frozen yet, forests of ferns and conifers burn. The smoke rises into the sky, joins the debris cloud, blocks out the sun. The temperature starts to drop. Here's the thing about the shockwave. It's not just destruction. It's the beginning of a cascade, a chain reaction that will last for years. The fires pump smoke into the atmosphere. The debris blocks sunlight. The temperature falls. Photosynthesis stops. Plants die. Herbivores starve. Carnivores run out of prey. But that comes later. Right now, in the first hour after impact, the shockwave is still spreading, still killing, still transforming the planet. At 4,000 miles, animals look up at a darkening sky. They don't understand what they're seeing. How could they? Nothing like this has ever happened before. A herd of Ankylosaurus, armored dinosaurs, stands in a clearing. Their backs are covered in bony plates, spikes along their sides, massive clubs on their tails. They're built like tanks, designed to survive attacks from T-Rex. But they're not designed for this. The debris falls, the fires start, the smoke rises. They stand there, confused, waiting for it to make sense. It never does. The shockwave circles the planet in 6 hours, a wave of pressure moving through the atmosphere. By the time it completes its journey, it's barely a breeze, a whisper. But the damage is done. Half the planet is on fire, the other half is about to be. The debris keeps falling, the smoke keeps rising, the sky keeps darkening, and the sound, the actual sound of the impact, is still travelling, still moving outward at the speed of sound. Animals on the far side of the planet will hear it tomorrow. A roar from across the world, a death scream from the Cretaceous period itself. But by then, most of them will be dead. The shockwave was just the beginning. The fires start everywhere at once, not from the impact itself. That's already happened. The shockwave has passed, but now the sky is raining fire. Remember those trillions of molten rock droplets, the ones that shot up into space when the asteroid hit? They're coming back down. Each one is small, marble-sized, but they're hot, over 1,000 degrees, and there are so many of them that they blanket the entire planet. Scientists call them spherules, tiny glass beads created when vaporized rock cools in the upper atmosphere. They're beautiful if you look at them under a microscope, perfect spheres, frozen droplets of the apocalypse. But falling from the sky at terminal velocity, they're weapons. The first ones land in the forests. A redwood tree in what will become California gets hit by a dozen spherules in 10 seconds. Each one burns through the bark into the wood. The tree has been standing for 800 years. It's survived fires before, lightning strikes, droughts, ice storms. This is different. The spherules keep falling, hundreds now. The tree's bark catches fire in a dozen places at once. The flames spread, merge. Within minutes the entire trunk is burning, and it's not alone. Every tree in the forest is being hit, every bush, every fern. The whole landscape is being pelted with fire from above. The forest ignites, not slowly, not tree by tree, all at once, like someone threw a switch. A herd of Alamosaurus, long-necked sauropods, tries to run. They're huge, 60 feet long, weighing 30 tons each, the largest land animals on the planet. They can't outrun fire. The smoke gets them first. Thick black clouds rolling through the trees. The Alamosaurus breathe it in, cough, stumble. Their lungs fill with ash and superheated air. One falls, then another, then the whole herd. They die where they collapse. The flames arrive minutes later and consume the bodies. In the ocean, the spherules hit the water and create steam. Imagine dropping a red-hot marble into a bathtub. The hiss, the bubble of steam. Now multiply that by 1 trillion. The ocean surface looks like it's boiling. A mosasaur surfaces to breathe. The air above the water is filled with steam, so thick she can't see. She breathes it in. It scalds her lungs. She dives again, tries to escape underwater, but the spherules keep falling. They sink through the water, still hot, creating trails of bubbles. The ocean temperature starts to rise. Fish near the surface die first. The heat kills them. Their bodies float, thousands of them, millions. The water is thick with corpses. Deeper down, other creatures feel the change. The water is getting warmer, not much yet, just a degree or two. But it's rising. They swim deeper, away from the heat. But there's nowhere to go. The spherules are falling everywhere, across every ocean, every sea. On land, the fires merge into firestorms. Here's how a firestorm works. Multiple fires burning close together create their own weather. The heat rises, creates a vacuum at ground level. Air rushes in to fill it. This creates wind, strong wind, which feeds the fires, makes them burn hotter, which creates more heat, more vacuum, more wind. It's a feedback loop, self-sustaining, unstoppable. The firestorm in what will become North America covers 10,000 square miles. The flames reach 300 feet high. The wind at ground level blows at hurricane force. Nothing survives inside a firestorm. The temperature at the center reaches 1,500 degrees, hot enough to melt glass, boil metal. Animals caught at the edge try to escape, run from the flames, but the fire moves faster than they can. Driven by the wind it creates. A pack of Dromaeosaurus, raptor-like predators, sprints through the smoke. They're fast, built for speed, can run 35 miles per hour in short bursts. The fire behind them moves at 40. They die running, overcome by smoke. Lungs seared, bodies charred. The fires burn for weeks. Not everywhere. Some places get lucky. A rainstorm in what will become Argentina puts out the fires before they spread. A river in Asia acts as a fire break, stops the flames from crossing, but most of the planet burns. The smoke rises into the atmosphere, joins the debris cloud already there. The sky gets darker and darker. By sunset on the first day, though you can barely tell it's sunset, the sun is just a dim red circle, like looking at it through thick fog. By the second day, you can't see the sun at all. The temperature starts to drop. This seems strange. The planet is on fire. How can it be getting colder? But fire needs oxygen, and oxygen needs plants, and plants need sunlight. The smoke and debris block the sun. Photosynthesis stops. Plants start dying. And when the fires burn out, when there's nothing left to burn, the smoke remains. Hangs in the atmosphere, keeps blocking the sun. The temperature falls fast. 10 degrees in the first week, 20 degrees in the first month. Antarctica, which isn't frozen yet, starts to freeze. But that comes later. Right now, in the first hours after impact, the world is still burning. A Pachycephalosaurus stands on a hillside, watching the forest below turn into an inferno. She's a dome-headed dinosaur, built for head-butting contest with rivals. Her skull is 10 inches thick, solid bone. It won't save her. The fire climbs the hill, slow but steady. She backs away, keeps backing up, until there's nowhere left to go. The hilltop is an island in a sea of flames. She dies from the heat before the fire reaches her, just stands there, breathing smoke, until she can't breathe anymore. In the burrows underground, some animals survive. Remember the protoceratops from earlier? The ones who hid when the debris started falling? They're still down there, huddled in the dark, listening to the world burn above them. The earth insulates them, keeps them cool, safe, for now. But they can't stay underground forever. Eventually they'll need food, water, and when they emerge they'll find a world transformed. Everything green will be gone, burned or buried under ash. The sky will be dark, the air will be cold. Most of them will starve within weeks, but some will survive. Small animals, burrowers, creatures that can eat almost anything, insects, seeds, roots, dead things. These survivors will inherit the Earth, but not yet. Right now, the planet is still dying. The fires spread to the polar regions, places that have never burned before. The Arctic forests, yes, there were Arctic forests, ignite. Ancient trees that grew in 24-hour summer sunlight burn in 24-hour summer twilight. The ash from these fires travels on the wind, circles the globe, adds to the darkness. By the end of the first week, the entire planet is covered in a layer of ash and soot. It settles on everything, coats the ground, fills the oceans, turns the ice caps grey. Geologists will find this layer millions of years later. A thin black line in the rock, visible all over the world. The boundary between the Cretaceous and Paleogene periods. The KPG boundary. The line that marks the day the dinosaurs died, but they're not all dead yet. Some dinosaurs survived the fires, the ones in the right place at the right time, near water, in clearings, underground. They emerge into a changed world. The sky is black, the sun is gone, the temperature is dropping. They don't understand what's happening. How could they? They're just trying to survive, find food, stay warm. A T-Rex wanders through the ash. Hungry. He hasn't eaten in days. There's nothing to hunt. All the prey animals are dead or hiding. He finds a corpse, another dinosaur. Burned. He doesn't care. He's hungry enough to eat anything. This is what the king of the dinosaurs has been reduced to. A scavenger. Eating the dead. He'll survive another week. Maybe 2. Then he'll starve. The last T-Rex dies alone. In the dark. Hungry. But in the moment, in this first day after impact, the fires are still burning. The debris is still falling. The world is still ending. And somewhere, deep underground, a small mammal huddles in its burrow. Waiting. Surviving. 66 million years from now, its descendants will stand upright. Build cities. Invent language. Tell stories about the day the world caught fire. But right now, it's just trying not to die. The fires burn on. The smoke rises. The sky darkens. And somewhere above it all, beyond the smoke and ash, the stars shine. Indifferent. Eternal. They've seen this before. We'll see it again. Worlds end, life continues. The universe doesn't care, but we do, we remember. We tell the story, because that's what survivors do. The darkness comes fast, not all at once, not like flipping a switch, but fast enough that you'd notice if you were watching. The debris cloud spreads outward from the impact point, a wave of dust and ash moving through the upper atmosphere, carried by winds, pushed by the heat rising from below. Within 6 hours it covers North America. Within 12 hours it reaches Europe and Asia. Within a day it circles the entire planet. The sun dims, then disappears. Think about the worst storm you've ever seen. The sky turns grey, dark. Heavy clouds block the light. You can barely see across the street. Now imagine that storm never ends. The clouds never break. The sun never comes back. That's what happens to Earth. The debris isn't just dust. It's everything the impact threw into the sky. Vaporized rock, ash from the fires, sulfur from the seafloor. Tiny particles of glass created when molten rock cooled in the upper atmosphere. Scientists call these particles aerosols. They're incredibly small, so small they stay suspended in the air for months, years even, and they're everywhere, trillions upon trillions of them, forming a layer in the stratosphere, blocking sunlight. The temperature starts to drop, not right away. The first day is actually hot, all those fires burning, the debris cloud trapping heat like a blanket. But then the fires burn out, run out of fuel, and the debris remains, hanging in the sky, blocking the sun. The heat escapes into space. Nothing replaces it. The temperature falls 10 degrees in the first week. A triceratops stands in what used to be a forest. Now it's just ash, burned stumps. The ground is still warm from the fires, but the air is getting cold. She's hungry. There's nothing to eat. All the plants are gone, burned or buried. She walks, looking for green. Anything green. There's nothing. The sky above her is the colour of charcoal. Not black, not grey. Something in between. A sick, yellowish brown when the sun tries to break through, which it doesn't. Not really. She can see maybe 50 feet. After that everything fades into haze. Other triceratops wander nearby, a small herd. They stay together after the fires, safety in numbers maybe, or just habit. They're all starving. One of them finds something, a fern that somehow survived, growing in a crack in the rocks, protected from the fires. The triceratops eats it in 3 bites, then keeps looking. There's nothing else. In the ocean, things are worse. The spherules that fell into the water brought heat. Lots of it. The surface temperature spiked. Fish died. Coral bleached and died. Plankton died. Plankton are tiny, microscopic, easy to ignore, but they're the foundation of the ocean food chain. Everything else depends on them. And plankton needs sunlight. They photosynthesize, just like plants on land. But the sun is gone. The plankton die within days. Billions of them. Their bodies sink to the ocean floor, create a layer of dead organisms that will become rock millions of years later. The fish that eat plankton starve next. Then the fish that eat those fish. Then the mosasaurs and plesiosaurs at the top of the food chain. A mosasaur swims through dark water. She's 30 feet long, built like a crocodile mixed with a whale. She's been hunting these waters for 15 years. She can't find anything to eat. The water is murky, full of debris. Dead fish float everywhere. She tries eating them, but they're rotting, make her sick. She needs live prey, something fresh. There's nothing. She swims deeper. Maybe there's food in the depths, away from the surface chaos. But deep water fish are dying too. The whole ecosystem is collapsing top to bottom. She surfaces one last time, breathes, The air smells like sulfur, like burning. She dives, keeps swimming, getting weaker. On land, the cold intensifies. 20 degrees below normal now, dropping further every day. Rain. Falls. Cold rain. Almost sleet. It washes ash out of the sky, turns the ground into grey mud. A herd of hadrosaurs huddles together for warmth. Duck-billed dinosaurs. They're built for eating plants. Their teeth are designed for grinding vegetation. There's no vegetation left. They stand in the rain, shivering, their body temperature dropping. Dinosaurs aren't cold-blooded. Scientists figured this out decades ago. They're somewhere in between, not quite warm-blooded like mammals, but not cold-blooded like lizards. They can regulate their temperature, to a point, but they need food for that. Energy. Calories to burn. They have no food. One of the hadrosaurs collapses, just lies down in the mud, too weak to stand. The others keep standing. For now. In the Arctic, snow begins to fall. This is new. The Arctic has been warm for millions of years. Forests grow there. Dinosaurs live there year-round. Not anymore. The temperature drops below freezing. Stays there. The first snow is light. Just flurries. Melts when it hits the ground. But more comes, and more. The ground is too cold now. The snow sticks. Within a week, there's 6 inches of snow covering what used to be forest. The dinosaurs there have never seen snow. Don't know what it is. They try to walk through it, find food, but there's nothing. Just white covering everything. They die in the cold. Bodies freeze, will stay frozen for millions of years until the ice melts and someone finds them. Back at the impact site, something strange is happening. The crater is enormous, 100 miles across, 25 miles deep at the center. But it's not empty. Water is flowing back in, the ocean rushing to fill the hole, creating a temporary sea inside the crater. The water is hot, boiling in places. The rocks below are still molten, still cooling. Steam rises, mixes with the debris cloud, makes everything worse, and the crater is still settling. The Earth's crust is broken here, fractured, pieces are sliding, adjusting. This creates earthquakes, big ones, magnitude 8, magnitude 9. The shock waves travel through the planet, trigger more earthquakes thousands of miles away. Volcanoes that were dormant wake up. The impact cracked the crust in multiple places. Magma finds new paths to the surface. In India, the Deccan traps are already erupting. Have been for thousands of years. Massive lava flows covering hundreds of thousands of square miles. The impact makes it worse. The eruptions intensify. More lava, more ash, more sulfur dioxide pumped into the atmosphere. The sky gets darker. The temperature keeps falling. 30 degrees below normal now. In what will become Montana, a T-Rex walks through ash drifts. He's the largest predator on the continent, the apex of the food chain. He's starving. There's nothing to hunt. All the prey animals are dead or dying. He's been eating corpses, anything he can find. But the corpses are running out, and he needs a lot of food. A T-Rex's size needs about 40 pounds of meat per day. He hasn't eaten in a week. His body is consuming itself, burning muscle for energy. He's getting weaker. He lies down, too tired to keep walking. The rain falls on him, cold, steady. He doesn't get up. Somewhere, a small mammal emerges from its burrow. It's been hiding underground for days, waiting for the chaos to end. The world above is different now. Dark, cold, covered in ash. But the mammal doesn't care. It's built for this. Small, efficient, can eat almost anything. It finds seeds buried in the ash, digs them up, eats them. It finds insects, still alive, hiding under rocks. It survives. This is the key difference: size. Big animals need lots of food. When food disappears, they die fast. Small animals need less, can survive on scraps, on things big animals would ignore. The dinosaurs are too big, too specialized, too dependent on a world that no longer exists. The mammals are small, flexible, adaptable. They'll inherit what's left, but not yet. Right now, they're just trying to survive. One day at a time. The darkness lasts for months. Some scientists think it was 6 months. Others say a year, maybe longer. The debris slowly settles out of the atmosphere, falls as rain, as snow, covers the ground in a grey layer. You can see this layer in the rock record, all over the world, a thin line of iridium-rich clay, the KPG boundary. Below that line you find dinosaur fossils, lots of them. Above that line, nothing. The dinosaurs are gone. The sun eventually returns, weak at first, filtered through haze. But there, the temperature starts to rise, slowly. But the world is empty now, silent. The forests are gone. The grasslands are gone. The oceans are dead zones. It will take millions of years for life to recover, to rebuild, to fill the empty spaces, but it will recover. Life always does. The survivors spread out, adapt, evolve. The mammals grow larger, take over. The niches left by dinosaurs. Birds, the only dinosaurs that survived, diversify, spread across the planet. 10 million years later, you wouldn't recognize Earth. The dinosaurs are a memory preserved in stone. The mammals rule. But in this moment, in the darkness after impact, none of that is certain. The world is dying. The future is unclear. All anyone can do is survive. Another hour, another day. Trust that the sun will return. It will, eventually. But first, the darkness. A week after the asteroid strikes, the world is cold, dark, and broken. But what does the evidence actually show about this time? It's easy to picture dinosaurs just dropping where they stood, but the real story is messier and stranger. If you dig into the rocks from this era, you start to see patterns. Layers of clay full of rare metals and tiny glass beads lie buried under our feet. But the details hidden in those rocks tell us about the first week after impact. They show us what it was really. Like, let's break it down. Start with the plants. On land, almost all the forests are gone, not just burned but stripped bare. In some places the soil itself is scorched, baked into hard crusts by heat and fire. Fossil pollen gives us clues. When scientists study the pollen grains trapped in rocks right above the impact layer, they find something odd. Almost no tree pollen. Instead, they see a sudden spike in fern spores. This is called a fern spike. Ferns are tough. They grow back after disasters. When fires wipe out everything else, ferns move in first. So, when you see a thick layer full of fern spores, it means the forests were wiped out and only ferns could grow. But what about the animals? Most of the big plant eaters vanished from the record. Their bones just stop appearing above that thin clay layer. The same goes for most of the giant meat eaters. T-Rex, Triceratops, Ankylosaurus, all gone. But some things survived. Tiny teeth, bones and burrows start showing up. More often, these belong to mammals, lizards, and a few birds. Most of them are small. Many are no bigger than rats or mice. They lived in holes, or under rocks, or deep in the forest floor. They could eat seeds, insects, or even dead things. That variety kept them going. Now let's talk about the oceans. We already know that plankton died off fast. But what does that look like in the rocks? In certain places you can see the switch. Below the boundary there are thick layers of chalk. White, soft stone made from the bodies of plankton. Above the boundary that chalk stops. Instead, you get a thin, dark band. This is called the KPG boundary. In places like Denmark, New Jersey and Spain, it's only a few centimeters thick, but it's the same all over the world. Inside that band are tiny glass beads, spherules, little bits of the asteroid frozen forever. In the ocean mud just above this layer, there are hardly any plankton shells. The few that remain are small and simple. They're the survivors. Everything else is gone. The same thing happens with fish and marine reptiles. Their fossils just stop. It's like someone flipped a switch. One day the seas were full of life. The next, almost everything was gone. But let's get more specific. In the Hell Creek Formation in Montana, there's a stretch of rock that covers the last days of the dinosaurs. Paleontologists have dug through these layers inch by inch. Just below the impact layer, they find dinosaur bones, eggshells, and footprints. Above it, nothing but scattered teeth and a few shell fragments. It's as if a curtain fell. The world changed in a single step. People sometimes wonder if the extinction took years, or even centuries. But the evidence points to something much faster. In North Dakota, at a site called Tanis, scientists found fish fossils mixed with glass beads and tiny bits of asteroid. The fish died with spherules in their gills. That means they were alive when the debris fell from the sky. Some were even buried next to tree trunks that were burned on one side. Everything happened in a rush. Fires, floods, and falling rock. The first week was a nightmare. Let's zoom in on that Tanis site for a minute because it's one of the best windows we have into this disaster. You can picture it, a riverbank full of life, when suddenly the ground shakes. Waves surge upstream, likely kicked up by giant earthquakes set off by the impact. Fish are tossed onto the shore, trees fall, and then, from the sky, comes a rain of glass and stone. Everything gets buried fast, so fast that some fish are still in the middle of swallowing their last meal. You can see their last snack, frozen in their stomachs. What about the air? In that first week, the air is thick with dust, ash, and chemicals. Scientists have found tiny sulfur crystals in the rocks from this time. These crystals form when sulfur gas cools quickly. The asteroid hit rocks full of sulfur, probably from ancient seabeds. When that sulfur blasted into the sky, it mixed with water vapor. The result was acid rain. The first drops might have fallen within days. That rain would have burned leaves, poisoned lakes, and made survival even harder. But we can get even more concrete. Let's look at temperature. Studies of fossil leaves show that the world cooled by at least 20 to 30 degrees, almost overnight. Some places went from warm green forest to freezing conditions in just days to weeks. In Antarctica, plant fossils show a sudden stop in growth rings. The pattern is sharp, no slow fade, just a hard line, like someone shut off the sun. In the sea, things are just as bad. Coral reefs bleach and die. The warm, shallow seas where ammonites and giant marine reptiles once thrived turn empty. Ammonite shells disappear from the record right at the boundary. A few stubborn species hang on, but they're gone within a year. Sharks and bony fish shrink in size. The survivors are tiny, fast-growing and able to eat just about anything. It's a world stripped down to basics. On land, fires and cold are just the start. With the sun blocked, photosynthesis stops. Plants can't make food. Without plants, the animals that eat them starve. The animals that eat those animals go next. It's a domino effect. Some scientists call this a trophic cascade, when one piece of the food chain collapses and brings down the rest. Simple idea, big consequences. But there's more. In lakes and rivers, mudslides become common. Without roots to hold the soil, rain washes dirt into the water. The rocks from this week are full of thick, messy layers, mud piled up on mud. Sometimes you even find logs all pointing the same direction. That tells you about huge floods, water rushing through burned forests, carrying everything in its path. The fossil record gets very quiet at this point. There are still bones and shells, but far fewer. Most of the animals you see are small. They're the disaster species, the ones that always show up after a big wipeout. Things like frogs, turtles, and early mammals. They burrow, hide, or hibernate. They don't need much food. They can wait out the hard times. One thing stands out: size matters. The bigger the animal, the harder it is to survive. Big dinosaurs, big marine reptiles, big flying pterosaurs, all gone. Smaller animals like birds and mammals have a better shot. If you're tiny, you need less food, and you can hide. If you can eat anything, you're golden. There's even evidence from eggs. Dinosaur eggshells disappear almost completely after the impact. Bird eggs, on the other hand, show up more often. Birds are a special case. They're dinosaurs, but with a few key advantages. They can fly, which helps them escape bad spots. Some can eat seeds, which survive fire and cold. It's not just luck, it's adaptability. Now, about the plants again. After the fires, the world is covered in ash and dust. The first plants to show up are ferns, as we saw. But after a while you start seeing pine needles and some hardy flowering plants. These are the pioneers, the first to colonize a dead world. They don't need much to survive. Over time, forests come back, but slowly. It takes thousands of years for the old mix of plants to return. Let's not forget insects. You might think they'd die off too, but some do just fine. Cockroach fossils are found above the impact layer. Beetles survive. Ants and wasps make it through, mostly by hiding underground or inside rotting wood. They're tough, and they don't need much light. What about the chemical clues? Scientists look for things like iridium, a rare metal that's common in asteroids but almost never found in Earth's crust. Right at the KPG boundary, you find a spike in iridium. It's like a fingerprint, showing that something from space hit the planet. In some places, the iridium level is 100 times higher than normal. That's how we know the event was global, not just local. Another clue is shocked quartz. Quartz is a common mineral, but when it gets hit by massive pressure, like from an asteroid impact, it changes. The crystals inside it get twisted and broken in a special way. You only see this kind of quartz at nuclear test sites or impact craters. Finding it in rocks all over the world is a smoking gun. And then there are the spherules. These tiny glass beads show up everywhere. In New Zealand, in Europe, in North America, places thousands of miles apart. They all match. Same shape, same makeup. They're pieces of the vaporized asteroid and Earth, cooled into glass as they fell back down. The fact that they're everywhere means the impact changed the whole planet, not just one spot. Let's talk about extinction rates. Scientists estimate that about 75% of all species went extinct in this window. That's 3 out of every 4 kinds of living thing. It's not just the famous dinosaurs, it's plants, insects, fish, reptiles, and more. Some groups, like the ammonites, lose every single member. Others, like sharks and crocodiles, make it through but barely. But extinction isn't just about numbers, it's about time. The fossil record shows that most of these losses happened quickly. Not over centuries, but in years or even months. It's hard to wrap your head around. Imagine walking through a forest one week and then coming back a month later to find nothing but stumps, mud, and silence. Some scientists have even found fossilized footprints right at the boundary. In places like Colorado and New Mexico, you see dinosaur tracks in mudstone. The next layer up, nothing. No tracks, no bones, no sign of life. It's a hard stop. Let's not forget about the sky itself. The air was loaded with carbon dioxide, sulfur, and dust. As the dust settled, the greenhouse gases started to build up. This created wild swings in climate. First, freezing cold, then sudden warming as the skies cleared. Plants and animals that managed to survive the cold were hit with new stresses. Some adapted, some vanished for good. One surprise: freshwater animals did a little better than those in the sea. Frogs, turtles, and some fish survived the first week. Maybe it's because rivers and lakes are smaller systems, less affected by ocean changes. Or maybe it's just luck. But their fossils keep showing up when everything else disappears. Let's talk about the mammals again, because this is their moment. Before the impact, mammals were mostly small, nocturnal and shy. After the impact, they start to spread out. In the first week, they're just trying to stay alive, eating seeds, hiding, waiting. But over time, their numbers grow. Their fossils become more common. They're the seeds of the future. But in this first week, nobody knows how things will play out. It's a world of ash, cold, and hunger. Every survivor is there because of luck, timing, or some tiny advantage. Being small, eating anything, hiding well. The evidence in the rocks is clear. This was not a slow fade. It was a sudden break, a line in history. People sometimes ask, could anything have survived if it was bigger? The answer is not really. The big animals needed too much food, too much space, and too much stability. When the world flipped upside down, there was no room for giants. Only the flexible, the hidden, and the lucky made it. And that's what the first week of impact winter was like. A planet in shock. Fires burning out. Cold settling in. Rain turning acidic. Food chains collapsing. Survivors digging in, waiting for the sun to return. But here's what gets me. You can hold a piece of this story in your hand. A bit of clay from the KPG boundary, a glass bead, a fossil leaf, all proof that this really happened. Not a myth, not a legend, a real disaster written in stone. And from those stones we learn something simple but important. Life is fragile but also tough. The rules can change overnight. The winners aren't always the biggest or the strongest. Sometimes they're just the ones who can hang on one day at a time in the dark. The world kept turning. The sun eventually came back. But in that first week, the planet was a different place. Cold, silent, waiting for what would come next. And as the first acid rains began to fall, the survivors faced yet another challenge. The story wasn't over, not by a long shot. If you want to picture what the first year after the asteroid was really like, you have to look closely, not just at dinosaur bones, but at tiny details buried in rock, mud, and even water. The story is still there, if you know where to look. It's not as simple as dinosaurs dying and mammals taking over. The real picture is more tangled and more grim. Let's break it down, one piece at a time. Start with the rain. Not just any rain, acid rain. This is one of the biggest shocks in the whole story. When the asteroid hit, it slammed into rocks packed with sulfur. That sulfur turned into gas and shot into the air. When it mixed with water vapor high above the ground, it made sulfuric acid. Then, as clouds formed and cooled, this acid fell back down to Earth as rain. It's hard to imagine, but this rain would have burned leaves, poisoned river water, and made the soil toxic. For plants just starting to recover from fire and ash, this was like another punch to the gut. Scientists have actually found chemical clues to this acid rain. In places like Spain and Montana, they studied fossil leaves from right after the impact. The leaves show holes, burns, and signs of chemical damage, not just from heat, but from acid. Some rocks from this time are full of minerals that only form when acid breaks down stone. Even the rivers change. You can see layers of clay that formed when acid rain washed minerals out of the soil and into the water. It's like the planet was being scrubbed raw. The proof doesn't end there. In places like Denmark, you find a strange pattern in fossil shells. Right below the impact layer, seashells are thick and normal. Above it, the shells become thin, pitted, and sometimes twisted. That's what happens when water turns acidic. Shells made of calcium carbonate start to dissolve. Small marine creatures, clams, snails, even tiny plankton, couldn't build strong shells anymore. Some didn't survive at all. It's a quiet kind of disaster. No explosion, no fire, just water slowly eating away at anything with a shell. But there's more going on in the oceans. When acid rain hit the sea, it changed the chemistry. The water became more acidic, and that made it even harder for life to recover. Think about coral reefs. They're made of calcium too. After the impact, reefs stop growing. Fossils show a gap. No new coral for thousands of years. The ones that did hang on were small and simple. Most of the big, branching coral vanished. Whole ecosystems went missing almost overnight. Scientists can track these changes in the rocks. In places like Texas and Tunisia, they find layers with almost no plankton fossils. The ones that do appear are tiny and plain. Before the impact, the sea was full of different shapes and sizes. Afterward, only a handful survived. Some areas go nearly empty for years. The few survivors are tough. They can handle low light, low oxygen and acidic water. Everything else is gone. On land, plants face a double threat, cold and acid. Remember, the sun is still blocked by dust and ash. Photosynthesis barely works. Even tough plants like ferns struggle. In some places, the fossil record shows gaps where nothing grows at all. No roots, no pollen, just bare soil. It's like the earth is holding its breath. But life doesn't give up easily. Some plants manage to come back, even if it's slow. Scientists find small amounts of certain spores, mosses, liverworts, and a few hardy flowering plants. These are the first signs of recovery. They don't fix the soil right away, but they start the process. Over time, they break up the hard crust left by fires and acid. They let water soak in again. They build up new layers of dirt bit by bit. Now, let's talk about the animals. Most of the big ones are gone, but not everything dies. This is where the evidence gets really interesting. In places like Montana and China, scientists find tiny burrows in the rocks just above the impact layer. These burrows are the right size for small mammals, lizards, and maybe even some bird chicks. Some are only as wide as a pencil. Inside, you sometimes find teeth, bones, or pieces of eggshell. What does this mean? It means that while the surface was a wasteland, life underground managed to hang on. Animals that could dig, hide, or sleep through hard times had a real advantage. Mammals, in particular, start to show up more often in the fossil record. Their teeth and jawbones become more common, even if the animals themselves are still small. But it wasn't just mammals. Frogs, salamanders, and turtles also leave their marks. These animals can wait out bad times by burrowing or slowing down their bodies. Some frogs can even survive being frozen. That's a superpower when the world is swinging between freezing cold and sudden acid storms. Birds are another clue. While most ancient birds vanish, a few lineages make it through. The survivors tend to be small, ground-dwelling, and able to eat seeds or bugs. These birds don't need much light or warmth. Some can fly long distances to find patches of green. Their eggs show up in small numbers, but they're there. Proof that not all hope was lost. Let's look at insects. You might expect a total wipeout, but the fossil record says otherwise. Certain tough insects like beetles, ants and roaches keep going. They're found in rocks from this time in places as far apart as Colorado, Argentina and Russia. Some beetles even seem to thrive in the chaos. They eat dead plants and animals, so a world full of rot is actually good news for them. There's even evidence in amber. Drops of fossilized tree sap from after the impact sometimes trap insects inside. If you look closely, you see a shift. Before the impact, you get a big mix of different bugs: flies, wasps, dragonflies. Afterward, the mix is simpler. Fewer types, but the ones that survive are everywhere. It's a new world, and only the flexible make it. Now zoom in on the rivers and lakes. Freshwater systems are weirdly lucky. In places like Alberta and Wyoming, you find layers of mud packed with the remains of fish, frogs and turtles. Some scientists think these animals did better because rivers and lakes recycle their water faster than the ocean. Acid rain still hurts, but it gets diluted more quickly. Plus, freshwater animals often live in burrows or mud where they're protected. But don't think it was easy. The evidence shows a drop in both the number and variety of fish. Some species disappear forever, others get smaller. Fossils from this time are often stunted. Fish that should be big are tiny, probably because there's not enough food. There are even fossil fish with twisted bones, possibly from acid or toxins in the water. Let's turn to the soil itself. After the fires, the ground is covered in ash and charcoal. When acid rain hits, it washes out important nutrients. Scientists have found layers where the soil is stripped of calcium, potassium and magnesium, minerals plants need to grow. The result is something called dead zones. Even when the sun comes back, plants can't recover right away. The soil is just too poor. There's a strange detail here. In some places you find bands of clay packed with little glass beads, leftover bits of the impact. Mixed in are crystals of a mineral called jarosite. Jarosite only forms in acidic conditions. It's rare on Earth, but common on Mars where acid weathering is normal. So when you see jarosite in these rocks, you know the ground was soaking in acid. The fossil record shows a change in how plants grow. Tree rings, the circles you see in wood, get thinner and sometimes stop altogether. In Antarctica, fossil wood from this time has a sharp line. Growth stops abruptly, then picks up again much later. It's like the trees went into shock. Animals show similar patterns. In some places you find fossil bones with lines that mark stress or starvation. These are called lines of arrested growth. They're like scars in the bone. They tell us the animal stopped growing, maybe for months, then started again if it survived. Most didn't. Let's talk about the oceans again, because this is where the biggest wipeout happens. Plankton, the tiny creatures at the base of the food chain, are nearly wiped out. In the rocks, you see a sudden drop in their fossils. The survivors are small, tough, and able to live on scraps. Some can even eat bacteria, but the big fancy plankton, gone. This has a ripple effect. Animals that eat plankton, like certain fish and small reptiles, start to vanish too. The fossil record shows a sharp drop in both numbers and diversity. Some marine reptiles try to hang on, but their fossils disappear within a year. Sharks and rays get smaller. Many types simply go extinct. You can even see the change in the mud at the bottom of the sea. Before the impact, it's full of white chalk made from plankton shells. After the mud turns dark, almost black and thin. It's called a black shale layer. It forms when dead plankton sink but nothing replaces them. The sea turns murky, low on oxygen, and full of dead zones. One of the best pieces of evidence comes from microfossils. These are tiny shells, sometimes smaller than a grain of sand. Scientists sift through tons of rock to find them. In the KPG boundary, you see a sudden change. Complex, branching, shells disappear. Only the simple round ones stick around. It's like someone hit the reset button on the ocean. But the story isn't just about what died. It's also about what survived. In the rocks above the impact layer, you start to see new kinds of fossils, not right away. It takes time. But eventually new types of plankton appear, different shapes, new ways of living. It's slow, but it's a sign that life is trying to come back. Let's get into numbers because they matter here. Scientists estimate that up to 75% of all species died out. In the ocean, it may have been even higher. Some estimates say 85% of marine species vanished. On land, most big animals were gone, but so were many plants, insects, and even fungi. It's one of the worst mass extinctions in Earth's history. But the pattern is strange. Some groups do better than others. Crocodiles, for example, survive. They can go months without eating, and they like murky water. That gives them an edge. So do turtles. They hide in mud, slow down their bodies, and wait. Mammals, birds, and a few reptiles hang on by being flexible, eating anything, hiding, or just getting lucky. Even the rocks themselves tell the story. In places like New Zealand, you find the same thin layer of clay packed with iridium and glass beads. In Africa, Asia, Europe, the same pattern. It's a global fingerprint. The impact didn't just change one part of the world, it hit everything, everywhere. Some scientists have even looked at fossilized poop, called coprolites from this time. The results are weird. Before the impact, coprolites are full of plant bits, bone fragments, and even insect shells. Afterward, they're mostly empty or full of charcoal and ash. It's clear that the food chain collapsed. Even the survivors were scraping by. There's another detail that stands out. In the years after the impact, rocks from riverbeds and lakes show huge amounts of mud and dead wood. Without plants to hold the soil, rain washed everything downstream. Whole valleys filled with silt and logs. In some places you find fossil log jams, piles of tree trunks all pointing the same direction, carried by floodwaters. It's a landscape in chaos. But even in the darkest layers there are signs of hope. New kinds of pollen appear, mosses and weeds start to spread, hardy insects return. In the rivers, new species of fish slowly take over. It's like the world is rebooting, one small step at a time. Scientists have tried to figure out just how long the recovery took. The answer depends on what you're looking at. For plankton, it's maybe 10,000 years before things are back to normal. For forests, it can take hundreds of thousands of years. For big animals, it's even longer. In some places, the old mix of species never comes back at all. The world after the impact is a different place. But here's the thing. The evidence doesn't just show a disaster. It shows survival. Every fossil, every chemical clue, every layer of mud tells a story, not just of loss, but of resilience. Life kept going, even when the odds were terrible. You can see it in the smallest details. A beetle trapped in amber, a stunted tree ring, a thin shell in acidic water. Each one is a piece of the puzzle. Together, they tell us what it's like when the rules of life change overnight. So, what does all this mean? It means that the planet was knocked down, hard. Acid rain, darkness, cold, hunger and chaos reigned. Most life forms didn't make it, but some did. Not because they were the strongest or the smartest, but because they could bend, hide, or just hang on. The first year after the asteroid was a time of endings. But it was also the start of something new. The survivors, tiny mammals, stubborn turtles, small birds, tough insects, became the ancestors of everything that came after. They set the stage for new worlds, new forests, and even, much later, creatures like us. That's the evidence. Not just a story about death, but a story about survival, written in stone, mud, and bone. The worst was over, but the hard work of recovery was just beginning. The world would never be the same, but it wasn't finished yet. The first decade after the asteroid was not a quick bounce back. It was more like a slow, uneven crawl. If you look at the evidence, you see a world that's damaged but not dead. Life is trying to come back, but it's patchy and fragile. Let's dig into what the rocks, fossils and chemistry actually show about these first 10 years. Start with the climate. Right after the impact, things were cold and dark. But over the next few years, the planet starts to change again. The dust and ash begin to settle. Sunlight returns, but not all at once. In some places, it's still dim for years. Places near the equator get light first. Farther north and south, the gloom hangs on longer. Scientists have found clues about this slow change in different layers of rock. In Wyoming, for example, you see a thin band of dark clay, then lighter layers above it. That shift is the planet waking up bit by bit. It takes about 3 to 5 years for the sky to clear enough for real plant growth to start again. But the weather is still wild. Temperatures swing back and forth. Some years are warm, others freeze unexpectedly. There are strange droughts and floods, probably because the normal patterns of wind and rain have been thrown off. This weird climate shows up in tree fossils. In Antarctica and New Zealand, trees that survived the impact show twisted, uneven rings. Some years they barely grow at all. Other years the rings are wider, maybe because of brief warm spells or sudden rain. It's clear that plants are struggling to adapt, but plants don't give up. The first decade is a time of pioneers, not big trees or lush forests, but small, fast-growing plants. Think mosses, liverworts, and ferns. Scientists call these disaster taxa because they are the first to move in after a catastrophe. They can handle poor soil, low light, and strange weather. Fossil pollen from this decade shows a spike in these tough plants. In Montana, Denmark, and even Siberia, you see layer after layer packed with fern spores. Other types of pollen are almost missing. This tells us that forests are gone, but open ground is covered by a green fuzz, ferns, moss, and a few weedy plants. Over time, a few flowering plants start to return. These are small, fast-growing species that can scatter lots of seeds. They aren't the same as the big trees from before. Instead, you find things like ancient relatives of dandelions, rushes, or sedges. These plants don't need much to survive. They spread quickly, covering bare ground and helping rebuild the soil. Let's talk about how long this fern world lasts. In most places it's at least 5 years, sometimes 10. Only after that do. You start to see the first hints of shrubs, then young trees. But it's not a forest yet. It's more like patches of scrubby growth with a lot of empty space between. Now what about animals? We already know that mammals, turtles, and some birds survived the first shock. But the first decade is when you start to see these survivors moving into new roles. The fossil evidence is thin, but it's there if you know where to look. For mammals, you see a gradual increase in the number and diversity of teeth and bones in rocks from this time. They're still small, mouse-sized, maybe rat-sized at best. But there are more kinds than before. Some have sharp teeth for eating insects. Others have flat teeth for grinding plants. A few show signs of burrowing, with strong claws and tough, compact bones. Here's a detail that sticks with me. In China, scientists found fossilized burrows from this decade, filled with tiny bones and teeth. Some burrows are reused over and over, layer after layer. It looks like mammals use these as safe spots, not just for hiding, but for raising young. That's clever. It's a way to stay alive while the surface is still risky. Birds are another group that begins to change in this decade. The big, flashy birds of the Cretaceous are gone, but small, ground-dwelling birds show up in new places. In Argentina, you find faint footprints in ancient mud, three-toed tracks left by birds hunting for seeds or bugs. Their bones are rare, but their presence is clear. Some birds even start to show changes in beak shape, maybe to eat the tough seeds and insects that are now common. Reptiles like turtles and crocodiles continue their slow comeback. Turtle shells are found in river mud in places like North Dakota and Alberta. They're smaller than before, but they're there every year. Crocodile teeth and scutes, the bony plates on their backs, show up in the same layers. Both groups seem to do best in the rivers and lakes, which are more stable than the battered land. Let's look at insects. In the first decade, the fossil record shows a strange pattern. Beetles, ants, and roaches are everywhere. They thrive in the chaos. Why? Because there's so much dead stuff to eat. Rotting plants, animal remains, even wood. Beetles especially do well. In amber from this time, you find beetles trapped with bits of ash and charcoal stuck to their legs. It's like they're cleaning up after the disaster. Some insects start to fill new roles. Pollinators, like early bees and tiny flies, are rare at first. But as flowering plants return, you see more of these insects in amber and mud layers. In places like Spain and New Jersey, scientists have found fossil pollen stuck to ancient bee legs, proof that the cycle of pollination is starting up again, even if it's slow. What about the oceans? The first decade is still rough, but little by little, life returns. At the start, the water is murky, acidic, and low on oxygen. Not much. Survives. But as the years pass, the chemistry slowly shifts. Rain washes out the acid. Sunlight comes back. Plankton, the base of the ocean food chain, start to reappear. Here's how we know. In places like Texas and Tunisia, the mud at the bottom of ancient seas changes colour and texture. At first it's dark and thin, almost black, but after a few years you see layers of lighter, chalky mud. These are filled with tiny round plankton shells. They're not the fancy branching types from before, but they're a start. It takes about 10 years for plankton to really bounce back in most places. Some areas recover faster, others lag behind. The first types to return are small, tough, and can handle low light and weird water. Over time, more types join in. This slow rise in plankton is key, because everything else in the ocean depends on them. Fish and other sea animals follow. The first decade is a tough time for fish. Fossils from this period are often stunted or deformed. Some fish are smaller than normal, with twisted bones or missing scales. But as plankton numbers grow, fish start to recover. New species show up, especially in rivers and shallow seas. Coral reefs, though, are still missing. They're one of the last things to come back. In the rocks from this decade, you don't see new coral growth. Instead, the old reefs are broken and buried under mud. It will be thousands of years before real reefs return. Let's talk about soil and land recovery. The ground after the impact is a mess, stripped of nutrients, packed with ash, and washed by acid rain. In the first few years, not much grows except ferns and moss. But life is persistent. As plants start to return, they slowly rebuild the soil. Their roots break up the hard crust. Dead leaves and stems add new layers of dirt. Worms and insects help mix things up, making the ground softer and better for new plants. In some places, you find thick layers of black soil built up over the decade. This is a good sign. It means the land is starting to support more than just weeds. Small shrubs and even a few young trees take root. It's not a full forest, but it's the start of one. Floods and erosion are still a problem. With so few plants to hold the soil, rain washes dirt and ash into rivers. In fossil riverbeds, you find huge deposits of mud, logs, and even animal bones swept in by floods. But as plants get thicker, erosion slows down. The land stabilizes and new habitats form. Now let's look at the chemistry. Rocks from this time are packed with clues. For example, you find layers full of jarosite, a mineral that only forms in acid. In the years after the impact, jarosite is everywhere. But as the decade goes on, it becomes rarer. This means the acid rain is fading, and the soil is getting healthier. Other minerals help tell the story. In Montana and Spain, rocks from this time show rising levels of calcium and potassium. These are key nutrients for plants. They're slow. Return matches the recovery of plant life on land. Another detail, in some places you see a spike in charcoal in the soil, even years after the impact. This tells us that wildfires kept happening, maybe every summer. With so much dead wood and dry plants, lightning could spark fires easily. Each fire cleared space for new plants, but also slowed the return of big forests. Let's not forget the rivers and lakes. These places are like oases in a broken world. Fossils from the first decade show a surprising amount of life in freshwater. Fish, frogs, turtles, and even small mammals leave their remains in the mud. Some lakes in Alberta and Wyoming are packed with tiny bones, teeth, and shells from this time. Why did freshwater bounce back faster? One theory is that rivers and lakes recover from acid rain more quickly. The water turns over faster so toxins don't linger. Plus, many freshwater animals can hide in mud or burrows, protecting themselves from bad times. Insects do, especially well in these places. Fossilized dragonfly wings, water beetles, and even early mayflies turn up in the mud. These insects help rebuild the food web, feeding fish, frogs, and birds. Let's zoom out and look at the big picture. The first decade isn't a dramatic comeback, it's a slow climb from rock bottom. The evidence shows tiny victories. Ferns spreading, beetles swarming, the first seeds sprouting. Each one is a step toward recovery. But the losses are still huge. Most of the old species are gone for good. The animals and plants coming back are different. They're tougher, smaller, and more adaptable. In a way, the world is being rebuilt by survivors. There's a lesson here about how life responds to disaster. It's not about strength or size. It's about flexibility, patience, and luck. The winners aren't the biggest or the most impressive. They're the ones who can make do with less, try new things, or just hold on long enough for things to get better. The rocks, fossils, and even the chemistry all point to the same story. The first decade after the asteroid is a time of struggle, but also of slow hope. Every small gain builds on the last. A patch of moss leads to a clump of shrubs. A single beetle becomes a swarm. A lonely bird track is followed by a flock. Some scientists have studied ancient DNA from this period. It's rare, but sometimes you get lucky. In a few places, fragments of genetic material are trapped in amber or frozen mud. They show surprising changes in the survivors' genes. Fast evolution. New traits, rapid shifts in how animals and plants live, eat, and grow. This kind of quick change is called adaptive radiation. It means that when the old world falls apart, the survivors try out new shapes, sizes, and ways of living. Over the next million years, this leads to whole new groups of animals and plants. But the seeds of that change are planted in the first decade. There's one last thing to notice. In the rocks, from this time, you sometimes find odd fossils, things that don't fit the old pattern. Tiny mammals with strange teeth, plants with weird leaves, insects that look almost modern, even though the world is still healing. These are the first signs that the future will look very different from the past. So the first decade is not just about bouncing back. It's more like a slow, stubborn rebuild. Every piece of evidence, rock, bone, spore, or shell, tells us that life didn't quit. It adapted, changed, and found a way forward. When you look at the story this way, recovery isn't a straight line. It's a series of small wins, long waits, and new beginnings. The big picture is messy but hopeful. The scars from the impact are everywhere. But so are the signs of life starting over. That's what the first decade after the asteroid teaches us. Even when the world falls apart, life keeps going. Not by going back to the old ways, but by inventing new ones. And that's how the planet took its first steps toward a new age, one slow year at a time. Now, let's see how those small changes set the stage for the next chapter, when life really starts to transform. When we talk about deep time, it's easy to let your mind slip. 66 million years is so far beyond anything we experience. It doesn't feel real. But deep time isn't just a big number. It's about slow change, layer by layer, year after year. After the first decade of recovery, Earth enters a new phase. This is when the real transformation happens, not in weeks or months, but in hundreds of thousands, then millions of years. The world doesn't snap back. It grows into something new. Let's dig into what actually changed and why those changes matter even now. To start, picture the land. After the first decade, plants have returned in patches, but forests are still missing in most places. For tens of thousands of years, landscapes look strange and empty, like a work in progress. In the fossil layers, you see hints of this. Tree pollen is still rare. Ferns and weedy plants are everywhere. Shrubs and small trees start to pop up, but real forests take much longer. In some places, it takes almost 100,000 years for large connected forests to return. That's longer than all of human history. Why does it take so long? The answer is complicated. Soil is a big reason. After the impact, the ground is stripped, packed with ash and sand. There aren't enough nutrients for big trees. Over thousands of years, plant roots slowly break up the crust. Worms and insects mix in dead leaves. Rain helps wash away toxins. Bit by bit, the soil becomes richer. Only then can the first hardwood trees, relatives of today's oaks and walnuts, begin to grow tall again. In places like Colorado and New Zealand, scientists have found fossil wood showing this slow return. The growth rings are thin and uneven at first, then get wider as the soil improves. Now think animals. The first survivors were small, mammals, turtles, and a few birds. Over deep time, these animals start to change. This is where evolution speeds up. With so many old species gone, there are empty spaces everywhere. Scientists call these ecological niches, jobs in nature that need to be filled. If a plant-eating dinosaur is gone, there's open space for something else to try that role. Same for predators, scavengers, and everything in between. What happens next is one of the wildest parts of the story. The small mammals that made it through the first decade begin to evolve quickly. Their descendants branch out in all directions. Some stay small and shrew-like, living in the undergrowth. Others get bigger. A few even grow to the size of pigs or small bears within a few million years. Scientists have found their bones in places like Montana and France. The teeth alone tell you everything. Some are sharp for eating insects or meat. Others are flat and perfect for grinded leaves or fruit. It's as if nature is running a giant experiment, trying out every shape and size. Let's talk about birds. The big ancient birds from before the impact are gone. But the survivors, small and ground-dwelling, start to change as well. Over time, they spread out and evolve into new forms. Some become what we would call modern birds. Others try new things, long legs for running, curved beaks for digging, even early versions of ducks and shorebirds. In places like Argentina and China, fossils show these changes happening step by step. Each new bird fills a gap left by the extinction. Reptiles also adapt, but in a different way. Crocodiles and turtles, which survived in water, slowly grow larger again. They move into lakes and rivers, taking on different diets. Some turtles develop tough shells for digging, while others become streamlined swimmers. Crocodiles in Africa and South America show new shapes, some long and narrow, others short and strong. These changes take hundreds of thousands of years, but once they start, they continue for ages. Now here's where things get interesting. The ocean has its own story. After the first decade, plankton and small sea creatures begin their slow comeback, but it's not fast. Coral reefs, for example, are wiped out almost everywhere. For at least 2 million years, there are no real coral reefs. Instead, the seafloor is covered with rubble, mud, and broken shells. Fish populations are small and scattered. Sharks survive, but many of the big ancient types are gone. But life in the sea doesn't stay simple for long. As plankton bounce back, everything else starts to respond. Over time, new groups of fish appear. Some look like today's salmon or herring. Small tough species do best. They become the base for new food chains. In the fossil layers from places like Morocco and Texas, you see more fish bones, teeth, and even scales as time goes on. It's a slow climb, but by about 5 million years after the impact, the oceans are starting to look busy again. One detail stands out: coral reefs. They're missing for a long time. Scientists call this the reef gap. For at least 2 million years, there's almost no coral building happening. The chemistry of the ocean is part of the problem. Acid levels are still high. It takes ages for rain, rivers, and ocean currents to wash out the chemicals left by the impact. Only when the water becomes stable again do coral polyps start to rebuild reefs. The first new reefs are small, scattered, and fragile. But once they get going, they spread quickly, creating homes for thousands of other species. Let's talk about insects. After the first decade, beetles and ants are everywhere. Over deep time, new insects evolve. Some specialize in pollinating flowers, others become leaf eaters or wood borers. In amber from this era, especially in Myanmar and the Baltic region, scientists have found fossil bees, wasps, and butterflies. Each one tells a story about how plants and insects work together to rebuild the land. Now, here's a theory that scientists discuss a lot. Why did mammals rise to dominate after the dinosaurs? Was it just luck or something else? Some researchers say it was about being small, warm-blooded, and flexible. Mammals could eat many things: bugs, seeds, roots. They could hide, burrow, and survive cold spells. When the big reptiles died off, mammals didn't just fill the gaps. They created new ways of living. climbing, swimming, gliding, even digging tunnels. Over deep time, these traits gave them the edge. But there's another angle. Some scientists suggest that the plants themselves shape the future. The quick return of flowering plants, angiosperms, gave mammals and birds new foods, seeds, fruit, and nectar. With new foods come new ways to live. Think about it. If you can eat both insects and fruit, you're more likely to survive in a changing world. Fossil teeth and stomach contents from this time show mammals trying out lots of diets. Some even ate fish or tiny crustaceans, a sign of just how inventive life became. Let's pause and think about the speed of change. Evolution usually seems slow, but after a mass extinction, things move fast. This is called adaptive radiation. It means that life branches out quickly, filling every open spot. In the rocks from places like New Mexico and Alberta, you can actually see this in action. Fossil layers go from simple, just a few types of small mammals or birds, to complex, with dozens of new shapes, sizes within a few million years. But not all places recover at the same pace. Some spots, what scientists call refugia, bounce back faster. These are special places where the damage was less severe. Maybe a river valley was protected by hills, or a patch of forest survived the fires. In these places, plants and animals had a head start. Over time, they spread out, helping to reseed. Other areas. In the fossil record, you sometimes find islands of old species that lasted longer than anywhere else. Another interesting pattern is how new groups appear in different parts of the world. Mammals in South America, for example, evolve separately from those in Asia or North America. The continents are drifting, but not yet in today's positions. This leads to strange animals, giant flightless birds in South America, odd-hoofed mammals in Africa, marsupials in Australia. Each place becomes its own laboratory for evolution. Now, here's something to think about. The extinction didn't just wipe out big animals, it changed whole ecosystems. For example, before the impact there were giant plant-eating dinosaurs everywhere. After, the largest animals are rarely bigger than a dog. This means that forests and grasslands grow differently. Without heavy footsteps and tree pushing, plants spread out in new ways. Over millions of years, this shapes the entire landscape. In some places, you get new types of forests. In others, open plains or wetlands. One theory says that the loss of big animals allowed flowering plants to take over. With less trampling and less grazing, small plants could grow tall and spread wide. This helped build richer soils and created new habitats for insects, birds, and mammals. In turn, these animals helped spread pollen and seeds, speeding up the recovery. Let's zoom in on the idea of innovation. After a disaster, nature doesn't just bring back the old world, it tries new things. Some mammals develop spines or armoured backs, others grow long fingers for digging. Early primates, tiny tree-dwelling mammals, appear in this era. Their hands and feet are built for grabbing branches. These small changes lead, over ages, to the rise of monkeys, apes, and eventually humans. Birds also try new ideas. Some lose the ability to fly, becoming runners like ancient ostriches. Others get better at flying long distances, crossing oceans or deserts. Insects invent new ways of pollinating flowers, carrying pollen on their legs or in special sacs. Even plants change. Some develop tough seeds that can survive fire or drought. Others create fruit to attract animals, who then spread their seeds far and wide. Over deep time, the climate itself keeps shifting. After the first cold years, things slowly warm up. But there are still swings, ice ages, warm spells, droughts, and floods. Life adapts each time. In the rocks from Wyoming and Germany, there are layers showing sudden warming events. In these layers you find bursts of new species. Sometimes even big mammals appear, like early hoofed animals or ancestors of horses. Here's another twist. The continents keep moving. Africa bumps into Europe. India crashes into Asia, raising the Himalayas. These slow changes create new mountains, rivers, and coastlines. Every shift gives animals and plants new places to explore. In South America, ancient rivers cut deeper canyons. In Australia, forests turn into deserts. Each change drives evolution in new directions. By about 10 million years after the impact, the world is packed with new life. Forests are thick again in many places. Grasslands and wetlands cover wide areas. In the sea, corals are back and fish are plentiful. Mammals range from tiny shrews to dog-sized predators. Birds fill the skies and the ground. Insects buzz everywhere. But the world is different. The old giants, T-Rex, Triceratops, giant marine reptiles, are gone. In their place are new giants. Elephants, whales, giant birds. Each one is shaped by the scars and lessons of the extinction. So what does all this mean? Here's what matters. Deep time isn't just about how long something takes. It's about how change builds on itself. One small victory, a patch of moss, a swarm of beetles, can set off a chain of events that reshapes the whole planet. Every survivor becomes the founder of something new. Every patch of healthy soil leads to a forest, then a home for animals, then a web of life that stretches across continents. There's also a lesson about resilience. Life doesn't give up. Even after the worst disaster, it tries again and again, testing new ideas, filling gaps, reaching for the light. The world that comes out the other side isn't the same as before. It's full of new possibilities, and there's something comforting in that. No matter how bad things get, change brings new hope. The world after the asteroid was nothing like what came before, but it was alive, creative, and always moving forward. I think about this sometimes, how the scars of disaster can turn into the roots of something amazing. The forests we see, the birds that sing, even the mammals that led to us, they all come from survivors who faced a world in ruins. They didn't just rebuild, they transformed. So when you look at a tree, a bird, or even your own reflection, you're seeing the legacy of deep time. You're seeing what happens when life refuses to quit. Everything around us is the result of those slow, stubborn changes that started after the asteroid. That's the real story of deep time transformation. Not just survival, but invention. Not just bouncing back, but becoming something new. And in a way, that's the story of all life. Always changing, always reaching, always finding a way forward. Now let's bring it closer, from the story of deep time to the world we live in, and what all this means for us right now. When you hear about the asteroid that ended the age of dinosaurs, it feels like ancient history. 66 million years ago. Impossible to grasp. But here's the wild part. It's not just some distant story about giant reptiles and strange plants. This is the moment that set the stage for everything around you. Your backyard, your pets, the birds at your window, even you. The world we live in, the shape of it, the animals in it, the fact that we're even here at all, comes out of that one day and what happened after. Let's break it down. Every living thing today is here because of a chain reaction that started with that impact. It's not just about dinosaurs disappearing, it's about what comes next. Imagine a reset button on the whole planet. Once the chaos faded and the dust settled, everything that survived had to figure out a new way to live. And over time, those choices, those struggles, shape the world you walk through every day. Think about mammals, your ancestors, not just humans, but all mammals, mice, dogs, Elephants, whales, they were tiny back then. Most could fit in your hand. They survived by hiding, digging, scurrying in the dark. When the world changed, these small survivors didn't just keep doing what they always did. They adapted. They tried new things. Some grew bigger. Some started to eat new foods. Some learned to climb, swim, or glide. This is where it gets personal. The only reason mammals got their big chance was because the old rulers were gone. If the asteroid had missed, dinosaurs probably would have kept running the show. Mammals might have stayed small and secret forever, but disaster made space for new ideas. Over millions of years, those little mammals spread out. They tried every possible lifestyle. Some became fast runners, some turned into swimmers, some took to the trees. Eventually, some learned to live in groups, care for their young, and even use simple tools. Here's a weird thought. The shape of your hand, the way your thumb moves, the fact that you can grasp things, that's a gift from those early mammals. They were experimenting with ways to live in trees, holding on tight, picking fruit. Those little changes passed down and improved led to hands like yours. Now let's talk about the birds you see today. Every sparrow, crow, or pigeon you notice is a link to the survivors of the asteroid. Not all birds made it. The giant ones, the ones that couldn't fly well, went extinct. Only the small, adaptable types survived. They learned to hide, to eat seeds and insects, to nest in places no predator could reach. Over time, some became experts at flying long distances. Others stayed close to the ground and learned to run. You might not think of birds as dinosaurs, but that's exactly what they are. The feathered creatures in your yard are the last branch of the dinosaur family tree. When you hear a robin sing or watch a hawk circle, you're seeing the legacy of a world that almost vanished. Let's bring it even closer. Why do we even have forests, fields, and grasslands the way we do? That's another result of the reset. Before the impact, huge plant eaters shaped the land. Dinosaurs like Triceratops and Ankylosaurus trampled trees, dug up roots, and kept forests open. After they vanished, smaller animals took over. They couldn't tear down trees or flatten grass in the same way, so plants grew taller, spread wider, and new types of forests and fields appeared. Think about this. The grass in your local park, the wildflowers along a road, the way trees cluster in groups, that all traces back to who was left standing after the disaster. Even the way soil forms, the spread of roots, and the thickness of forests are linked to the animals that came next. Without giant dinosaurs, plants got the freedom to try new things. They flourished, making more food for insects, birds, and mammals, which sped up the whole process. Now, let's zoom in on insects. Every bee, butterfly, or ant you've ever seen is part of this story. After the asteroid, insects exploded into new roles. They became pollinators for flowering plants, spread seeds, and broke down dead wood. This partnership between insects and plants is why you have fruit, nuts, and vegetables today. Apples, berries, even chocolate. None of it would exist without that rebound. And here's where it circles back to you. The food you eat, the oxygen you breathe, the animals you love, all come from that strange, broken world after the impact. Every meal, every breath, every walk in the woods is a direct line back to that moment when life had to start over. Let's take it a step further. Why do humans even exist? That's not just luck. It's a result of the new world that grew out of disaster. Early mammals, after the impact, started to branch out in wild ways. Some became predators, others became plant eaters. A few learned to live in trees, jumping from branch to branch, using hands and feet to grip and climb. Over millions of years, these tree-living mammals developed better vision, smarter brains, and more flexible bodies. That's the start of the primate family, the group that would eventually lead to monkeys, apes, and us. If the asteroid hadn't cleared the stage, it's possible primates would never have evolved at all. Or if they had, they might have stayed small and hidden, just another oddball branch, every part of being human. Your curiosity, your fingers, your eyes facing forward, comes from a chain of changes that began in a world recovering from disaster. Even your need for friends, for family, for connection is part of a survival strategy built millions of years ago. Animals that worked together did better. They protected each other, found food together, watched out for danger. That social side is baked into our DNA. Let's bring in another angle. Have you ever wondered why the world has certain animals and not others? Why are there elephants in Africa, kangaroos in Australia, or llamas in South America? It's because after the asteroid, continents drifted apart and survivors evolved separately. Each place became its own experiment. Some animals grew large, some stayed small, some learned to fly, others to swim. The variety of life you see today is a direct result of those separate journeys. Even the pets you know, dogs, cats, hamsters, are part of this long story. Dogs and cats come from ancient lines of mammals that survived the extinction. Their ancestors learned to hunt, hide, and live through change. Over time, they became the animals we know today. Let's talk about oceans for a minute. The fish you see in an aquarium, the whales and dolphins in documentaries, the crabs and starfish at the beach, these are the products of a new ocean world. After the asteroid, the seas were empty and strange. But as new life filled the gaps, fish diversified. Some became fast swimmers, others learned to hide in the sand. Mammals like whales and dolphins returned to the water, evolving from land animals that decided to try something new. Even coral reefs, which take ages to build, are part of this story. When you snorkel or watch a nature show, the colourful fish and bright corals are descendants of the first pioneers that rebuilt the ocean after the disaster. Without that reset, the reefs we know might never have formed. Now let's dig into something deeper. Why does this history matter to you right now? It's easy to think of mass extinctions as old news, but the lesson is about change and what comes after. The world we know is a product of survival, adaptation, and new beginnings. When disaster hits, it doesn't just destroy. It opens up new paths. That's what happened after the asteroid. Life didn't just recover, it invented, explored, and discovered what else was possible. We're living proof of that. The way you think, move, feel, and dream all come from a line of survivors who faced the worst and kept going. That's not just a story about ancient mammals. That's a story about persistence, curiosity, and the drive to keep moving forward no matter what. Think about your daily life. The breakfast you eat, the birds you hear outside, the grass under your feet, all connect back to that one moment when everything changed. If you look closely, the world is full of reminders of this history. The shape of a leaf, the song of a bird, the way animals care for their young, all are echoes of the choices and chances that shaped life after disaster. Even our fears and hopes tie into this deep history. Why are we scared of the dark or of loud noises? Maybe because long ago those instincts kept our ancestors alive during dangerous times. Why do we feel comfort in groups or find joy in sharing food? Because that's how early mammals survived after the world went dark. Here's what gets me. Every living thing today is here because of a long line of survivors. Your family tree doesn't start with people. It goes back through mammals, through tiny shrew-like creatures, all the way to something that scurried in the undergrowth after the asteroid hit. That's wild to think about. You're the result of not just luck, but the stubbornness of life to keep trying. Let's talk about resilience. Nature is full of setbacks and comebacks. The asteroid was the worst day in Earth's history, but it wasn't the end. It was a beginning. Life found cracks to slip through. It tried new shapes, new ways of living. Some ideas worked, some didn't. But enough did that the world became rich and full again. That's a lesson for us too. No matter what happens, there are always new paths forward. Even the way we change as people, how we grow after hard times, how we find meaning in struggles, mirrors the story of life on Earth. Setbacks force us to adapt. Hard times make us rethink who we are. Just like those first mammals, we become something new by surviving what seems impossible. Now, let's look at the bigger picture. The asteroid didn't just affect animals and plants. It changed the land, the air, the oceans. It set off a chain of changes that shaped the climate, the continents, even the way seasons work. The world you see on a globe, the shape of Africa, the mountains in Asia, the rivers in America, these are partly the results of what happened after that day. Volcanoes erupted, mountains rose, oceans shifted. Over tens of millions of years, these changes gave animals new places to live. Some moved into forests, others onto plains or into mountains. Every change created new challenges, and every challenge led to new inventions in nature. The lesson is simple but powerful. The past isn't just something that happened to someone else. It's inside you, part of your story. When you walk outside, breathe in the air, or look at the stars, you're part of a chain that began long before you were born, and every day you write a new line in that story. If you ever feel small or lost, or wonder if what you do matters, remember this. You're the product of survival, of hope, of trying again when things seem broken. That's the real legacy of the day the dinosaurs died. Not just an end, but a beginning that led all the way to you. So next time you hear a bird sing, watch a squirrel climb a tree, or just enjoy the feeling of sun on your face, know that you're sharing this world with the echoes of deep time. Everything around you, the life, the beauty, even the struggles, comes from that moment when the world started over. You're part of that story. You always have been, and every day you carry it forward just by being here. Here's something to think about. When people talk about the end of the dinosaurs, they usually focus on the disaster itself, the impact, the fires, the darkness. But the real story is what comes after. Not just for animals and plants, but for the planet itself. The world didn't just recover, it became something totally different. That's what set the stage for everything we know. Picture the ground right after the worst of it. Not just burned or empty, but full of new possibilities. The surface of the Earth was changed in ways you can still see today. If you dig deep into the rocks, you can find a thin layer of clay, packed with a rare metal called iridium. It's not common on Earth, but it's found in asteroids. That layer is like a bookmark in time. Geologists use it to spot the moment everything changed. It's in North America. It's in Europe, Asia, Africa, even Antarctica. No matter where you look, that line is there. Now imagine walking through a forest, millions of years after the event. The trees aren't the same ones dinosaurs saw. The soil is richer, full of new minerals and nutrients. That's because the impact stirred up the deep layers of Earth. It spread ash and dust that over time broke down and fed the next waves of plants. Even today, Some of the richest soils grow where ancient disasters happened. Let's talk about rivers. Water is always moving, always shaping the land. When the asteroid hit, it created shock waves that changed the course of rivers. Old riverbeds filled with ash and debris. New channels formed as water carved its way through fresh landscapes. This reshaping helped create places where new kinds of plants and animals could start over. Coastlines shifted too. Some places sank, others rose up. If you look at maps made by geologists, you'll see that the shapes of continents and oceans changed after the impact. Sometimes the clues are buried deep, layers of rock that only show up when you break open a cliff or dig a well. But the fingerprints are everywhere. Here's something wild. Some scientists think the asteroid's shock waves may have helped trigger volcanic eruptions far away, not right away, but over years or decades. In India, a region called the Deccan Traps was already erupting before the impact. After the asteroid, the eruptions got stronger. Layers of lava poured out, covering an area as big as Texas. The heat and gases from these eruptions added more stress to a world already in chaos. The evidence is in the rocks. Lava flows from this time are thick, stacked one on top of another. If you walk across the Deccan Traps today, you're standing on the remains of those ancient eruptions. The timing is close, a few 100,000 years, maybe less. Some researchers debate which disaster did more damage, the asteroid or the volcanoes. Most agree the asteroid was the main cause, but the volcanoes made things worse. Now, let's think about the air. When the asteroid struck, it put dust, ash and gases into the sky. But over time, as plants grew back and oceans mixed their waters, the air changed again. Oxygen levels dropped for a while, then slowly climbed. Carbon dioxide spiked, then fell. These swings forced animals and plants to adapt in new ways. Some creatures needed more oxygen to survive. Others found ways to live with less. The ones that could handle big changes made it through. The ones that couldn't vanished. Even today, sudden swings in air and water can test how tough a species is. You can see that story in the fossil record, but also in the animals and plants around you now. Now think about the sky. Not just the dust and darkness, but the way the stars must have looked during these long nights. For years, the nights were darker than anything you've ever known. No moonlight breaking through, no glow from cities. Just blackness, except for the stars. Maybe the survivors, small mammals, birds, insects, used that darkness to hide, to move, to start new lives. The night sky became a place of safety, but also of change. Some animals became more active at night, a pattern that lasted for millions of years. Even today, many mammals prefer the dark. Maybe it's a memory, deep in their genes, of a time when the day brought danger and night was the only safe time to move. Let's talk about timing. The impact happened fast, but recovery took ages. Some plants came back within years. Others needed thousands of years. Large forests took even longer, but every comeback was a step towards something new. The first animals to return shaped what happened next. They ate the first plants, spread seeds, dug burrows, and created shelter for others. Each small step made the world a little more livable. Now let's focus on the survivors. Not just mammals and birds, but also turtles, crocodiles, and even some fish. These animals found ways to ride out the chaos. Turtles can survive without food for months. Crocodiles hide in mud and wait. Fish in deep lakes or slow rivers kept going while everything above changed. These skills, waiting, hiding, surviving on almost nothing, are what saved them. Some of their descendants are still here. The turtle in your backyard, the crocodile in a zoo, the fish in a pond, They're living proof that patience and toughness matter. Here's a twist. The disaster didn't hit everywhere the same way. Some places near the impact were wiped clean. Other places far away lost fewer species. In places like New Zealand or Madagascar, plants and animals survived that disappeared elsewhere. These refuge spots became starting points for new lineages. Today, some of the world's strangest animals, like kiwis, lemurs, or tuatara, trace their roots to these safe zones. That pattern shows up in plants too. Certain forests in South America or Australia hold trees whose ancestors survived by luck and isolation. These pockets of life remind us that history isn't always fair. Sometimes survival is about being in the right place at the right time. Now, let's think about the lessons for today. The asteroid was a one-day event, but the world's story since then is about recovery, change, and invention. Every living thing is here because something before it adapted to a new world. That's not just about biology. It's about how life, in every form, finds ways to keep going. It's easy to feel like disasters are only about loss, but when you look closer, you see that every ending is also a chance for something new. The plants that rose from the ashes, the animals that tried new ways to eat or move, even the shapes of continents and rivers, all these things are proof that change can create room for invention. If you're ever tempted to think that the world is stuck or that nothing new is possible, remember this story. The biggest, most powerful animals vanished in a single day. But that wasn't the end. It was the start of a world full of opportunity for anything willing to try. Think about how that connects to people. Our own history is full of hard times and sudden shifts. Sometimes things fall apart. Sometimes the rules change overnight. Maybe your life has had moments like that. But the lesson from deep time is simple. Surviving isn't just about holding on. It's about changing, growing, and trying new paths. Now, consider the future. Earth will keep changing. There will be challenges, surprises, maybe even disasters. But the story of the asteroid shows that life is stubborn. Even when everything seems broken, there's always the chance for something unexpected to grow. That's why people study these old disasters, not just to know what happened, but to understand how recovery really works. It's slow, it's messy, it's full of setbacks and strange turns, but it also leads to new beauty, new forms, and new ways of living. The world outside your window is full of echoes from that ancient day. The colour of the grass, the shape of a bird's wing, the way a mammal nurses its young, all are results of changes that came out of disaster. Even the way forests grow, or how rivers wind across the land, have roots in the recovery that followed. Sometimes it's easy to forget how connected everything is, but every breath, every bite of food, every sound you hear at night is part of a chain that goes back through deep time. You're connected to turtles, birds, grass, and even the rocks under your feet. If you step outside and look up at the night sky, remember that the darkness once meant survival, that the stars once shone down on a broken world, waiting for the next chapter. Now those same stars shine on you, on forests and cities, on animals that are the result of all that change. We don't know what the next big change will be, but we do know that life finds ways to adapt. That's the real message of the day the dinosaurs died. Not just an end, but a new beginning. One that keeps unfolding, even now. So if you ever wonder about your place in the world, or if things can get better after hard times, remember this story. The world has started over before. Life has found a way, again and again. And you're here because of that long, wild history of survival and hope. In the end, the day the dinosaurs disappeared wasn't just about loss. It was about what came next, and what came next was everything.